Hi, I'm Ben-Yaakov. This presentation is entitled Economical Driver for an Open Winding Three-Phase Motor. In this video, I'm going to explain the idea behind this patent, published on October 2022, entitled Optimal Open Winding Inverter for Controlling Three-Phase AC Motor, and as it happens, I'm one of the inventors. So what is the issue here? I'm showing three ways of connecting a inverter to a three-phase motor. Say it's a BLDC, brushless DC motor. This is the classical connection. It's a star connection. This is a delta connection. And here we have the open winding. In this case, each one of the coils of the motor is driven by a separate full bridge. So in this case, we're going to have 6 half bridges as compared to the 3 bridges that we are going to have in the classical inverter. Okay? So why would you like to do that? Well, the reason relies on the issue of the high RPM range of a motor. I'm showing here a torque to RPM curve, and at high RPM there is a problem delivering torque to the motor at high RPM, and the reason is that at high RPM you have a high back EMF from the motor coming, and therefore you need a coil voltage which is higher than the back EMF. So you are limited by the battery and the type of connection. Why is it that the connection matters? Because the voltage that you'll have on the coil depends on the connection. The best situation is here. We have a full bridge driving a coil independently, and I'm going to discuss it a little bit later to find out the exact values, but clearly the voltage that you can get here across the coil is the highest. Here we do have the voltage between the 2 half bridges here, but they are shifted in phase 120 degrees, and consequently it turns out that the voltage here will be lower than here, and obviously here we are sharing this voltage between these 2 coils here, so therefore the voltage across each one of these will be lower. So let's see how we can estimate these voltages. I'm showing here a half bridge, and for simplicity I'm using here a split voltage, plus minus, and each one will be the total voltage over 2. By this, I'm getting here an AC voltage that is after modulation, and say assuming a modulation factor of 1, the peak value of the AC that can be generated with PWM modulation will be, of course, the VB over 2 plus and minus, so the peak value is VB over 2. Now, if I have 2 units like this connected across the coil, one coil, then by having these in opposite phases, that is 180 degrees, I can get the sum plus and minus, and consequently I'm going to get a peak value of VB. Okay, so this will be the best situation. On the other hand, if I'm looking at the delta case, indeed each one of these is delivering VB over 2 peak value of the AC, but there is a phase shift here 120 degree, and you can calculate that the voltage across the coil in this case will be 0.866 times VB, lower. Now we don't like this connection. The reason that we don't like it is because of the circulating current here, and this is because we have a series connection of the voltages, and any mismatch in these might cause a circulating current, so this connection is not preferred. What is preferred today is the star connection, so that you don't have the circulating current. Of course, there's some other issue which I'm not going into, and this is the connection that is used in most cases, especially in the brushless DC motor. And in this case, you can see that we have here again VB over 2, VB over 2, and here look at the symmetry, it's like a bridge, and consequently the voltage here is also VB over 2. So the peak value of a coil in this connection, due to the phase shift between these and the fact that the voltage is then divided between these two with a phase shift, of course, then it comes up to be VB over 2, which is the lowest of the three. So if I summarize these results, I find the following. For the open loop, I can get a peak value of the voltage of VB. For the delta, 0.866, which we don't like, as I have said, the delta. And for the star, it's only 0.5. So if I compare the open winding to the delta, there is a drop of 13% because there is a phase shift between any two half bridges. And the worst case is, of course, the star, and here I'm losing 50% as compared to the open winding. So clearly, the open winding gives you the highest voltage, and this is why it is preferred. But, of course, there's some problems with it, especially in the fact that it needs twice the number of transistors. That is, instead of 3 half bridges, you need 6 half bridges, which is quite a bit. And then you need control because these coils are independent, so you have to make sure that indeed the currents are 120 degree and the same magnitude. But this can be solved by a proper control unit. And then there is also a question of the third harmonic issue, which I'm not going into. So there are many issues with the open winding. The worst of them is, of course, the fact that you need twice the number of transistors. So this patent that I'm now explaining is aimed to reduce the number of transistors, and it is doing it knocking down from times 2 to 1.3, saving 2 half bridges, which is about 30%. So how can we do that? It is easily explained by considering a delta connection. But in this case, I'm opening here this connection here. Now, ideally, of course, if everything is fine, no problem, etc., then A and A prime would be exactly the same because it's the same point. Now, if, however, I'll connect them, then again, due to some asymmetry, some differences between the phases, and we might have a problem with this circulating current, and then some other issues that I'm not going into. By separating them and filling each one with a half bridge, I can actually control the value here. So I have another degree of freedom here to adjust the voltages. They might be not exactly, a little bit different, such that I can control the currents in the coils independently. So here it is, the scheme. We have the 3 coils. We have half bridge, which is kind of the reference, and then we have a half bridge which is operating with the first half bridge to generate a current which is sinusoidal, and this is the reference current. And then I have another half bridge which is working with this half bridge to generate a current which is of the same magnitude as here and phase shifted 120 degree. And then I have a third half bridge which again is controlling the current here with 120 degree phase shift. Now ideally the phase here, 360, is the same as the phase here, but this is when I'm connecting them. If I am not connecting them and this point is sort of can be independently controlled, it helps me to avoid the hard connection here and the loop that again will cause this circulating current. So in this case we have voltages which are like in the delta connection, because again I'm feeding here this voltage here between these 2 half bridges which are shifted by 120 degree, we'll see it, but I don't have a hard wire connection between these 2 ends. So actually it's an open winding configuration. So in terms of control, as I have said, we are controlling this half bridge with this half bridge to generate the, let's call it reference current, and then with this and this, it is controlling this current, which is supposed to be, I mean, if it's a symmetrical motor, supposed to be the same current but shifted 120 degrees, and again with this configuration. To simplify the explanation and to make it more intuitive, I've demonstrated the method of the 4 half-bridge inverter in terms of the sinusoidal modulation scheme. However, there are many other modulation methods available, and one of them is the space vector PWM modulation, which is very useful in this particular case. Here we are showing the waveform related to the space vector PWM modulation. This plot as well as this table were prepared by Stas, and I am very grateful for his contribution on that. So here we are showing the waveform that you'll get out of each of the half bridges, and here I'm showing phase, one of the phases here, the blue and the red, and in between we see the resulting sinusoidal waveform which we would like eventually to get. Now, in this particular case, the advantage of the space vector PWM modulation is that we are getting a maximum voltage of the bus voltage. So this is a very unique case, which then means that we are saving in terms of the number of transistors, but we are not losing anything in terms of the amplitude as compared to the very simple open winding with a full bridge for each one of the coils. This brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest. Thank you.